February 12, 1943. Henderson Field, Guadalcanal, Marine Fighter Squadron, 124, received delivery of their first Chance-Vought F4U Corsairs. The new fighters sat on the coral strip with their distinctive inverted gull wings creating an M-shaped silhouette against the morning sky. Ground crews walked around the aircraft shaking their heads. One crew chief was overheard saying, "The wings are on backwards. The damn things are going to fly in reverse." 2 days later, on Valentine's Day, those same Marines would take their strange-looking fighters into combat. 9 American aircraft would fall from the sky that afternoon. The loss ratio was 9-1 in Japan's favor. Japanese pilots radioed back to their bases with confident reports. The Americans had sent up another inferior design. The bent-wing fighter was nothing to fear, but the Japanese assessment would prove catastrophically wrong. Over the next 2.5 years, that peculiar inverted gull wing design would help Corsair pilots achieve something unprecedented in the history of aerial warfare. For every Corsair lost to enemy action, American pilots would shoot down 11 Japanese aircraft, 2,140 kills against 189 losses. The bent wings that Japanese engineers initially dismissed as a design flaw were actually the visible signature of engineering decisions that would revolutionize carrier aviation and create one of the most lethal fighters ever built. The story of how an unconventional wing configuration became the foundation for air superiority in the Pacific begins not with combat, but with an impossible specification that the United States Navy issued in February 1938. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The United States Navy Bureau of Aeronautics sent request for proposal number 1558 to American aircraft manufacturers on February 1, 1938. The specification was straightforward and seemingly impossible. Design a carrier-based fighter capable of exceeding 400 miles per hour in level flight. At that moment in aviation history, most fighters struggled to reach 350 miles per hour. The Navy was demanding a 50-mile-per-hour improvement over the fastest fighters in service, plus the ability to operate from aircraft carriers. The requirement included additional constraints that made the challenge even more daunting. Maximum speed must exceed 400 miles per hour. Landing speed must remain below 70 miles per hour for safe carrier operations. Combat range must reach 1,000 miles. Armament must include at least 450 caliber machine guns with adequate ammunition. The aircraft must carry provisions for bombs or external fuel tanks. Structure must withstand catapult launches and arrested carrier landings. Most American aviation companies studied these requirements and concluded they were contradictory. High speed demanded powerful engines and streamlined designs. Low landing speeds required large wings. Long range meant heavy fuel loads. Carrier operations imposed weight and strength penalties. Combining all these requirements in a single airframe seemed impossible. Chance-Vought Aircraft Division approached the problem differently. Their chief designer, Rex Beisel, held degrees in aeronautical engineering from Massachusetts Institute of Technology. His design team included some of the most talented engineers in American aviation. Rather than compromise between conflicting requirements, they decided to build the most powerful fighter possible and then solve the problems that power created. The solution began with an engine. Pratt & Whitney had recently developed the R2800 Double Wasp, an 18-cylinder 2-row radial producing 2,000 horsepower. This was nearly double the power of engines in contemporary fighters. Beisel's team decided to design their entire aircraft around this massive power plant. The decision created an immediate problem. To convert 2,000 horsepower into thrust, the aircraft needed a propeller 13 feet 4 inches in diameter. This was the largest propeller ever proposed for a fighter aircraft. A propeller of this size created ground clearance issues that conventional landing gear could not solve. If they used straight wings like every other fighter, the landing gear would need to be impossibly long to provide propeller clearance. Long landing gear meant heavy landing gear, which meant structural penalties that would eliminate the performance advantages they were seeking. The engineering team considered multiple solutions. They could use a smaller, less efficient propeller. This would sacrifice performance. They could design extremely tall landing gear. This would add unacceptable weight. They could position the engine higher in the fuselage. This would create aerodynamic problems and visibility issues for the pilot. Rex Beisel proposed a solution that seemed radical. Instead of raising the entire aircraft to clear the propeller, what if they lowered just the portion of the wing where landing gear attached? The idea evolved into the inverted gullwing configuration that would become the Corsair's signature feature. The design was elegant in its mechanical simplicity, the wing's center section attached to the fuselage at the highest point. From there, the wing angled sharply downward at an angle before leveling out for the outer wing panels. This created the distinctive inverted gull or bent wing appearance. The configuration solved multiple problems simultaneously. Landing gear attached at the lowest point of the wing's angle, allowing relatively short gear legs while maintaining propeller clearance. The downward angle at the wing root actually improved aerodynamics by creating a clean junction between wing and fuselage, with minimal drag. The cranked wing allowed the wing's outer panels to be perfectly horizontal, optimizing lift distribution. Most importantly, the entire structure could be made lighter than conventional alternatives because the landing gear attached at an optimal structural point. The aerodynamics department ran calculations that validated the concept. The inverted gull configuration would produce less drag than a conventional straight wing with tall landing gear. Wind tunnel tests at the California Institute of Technology confirmed that the unusual wing shape actually improved airflow around the wing fuselage junction. Structural engineers analyzed stress loads during carrier operations. The cranked wing design distributed forces efficiently, allowing lighter construction without sacrificing strength. The engineering solution was sound, but it created manufacturing challenges that would test American industrial capability. Creating the compound curves of an inverted gullwing required sophisticated tooling and precise quality control. Each wing had to be built to exact specifications, or the two wings would not match, creating asymmetric flight characteristics. Japanese aviation engineers would later study this design and conclude that while theoretically sound, it exceeded their manufacturing capabilities in wartime conditions. The prototype F4U-1 first flew on May 29, 1940, piloted by Lyman Bullard Jr., Vaught's chief test pilot. The flight was conducted from the factory airfield in Stratford, Connecticut. Initial results were promising but revealed development challenges ahead. On October 1, 1940, during a high-speed test flight between Stratford and Hartford, the XF4U-1 achieved 405 miles per hour ground speed with tailwind assistance. The aircraft made headlines as the first single-engine American fighter to exceed 400 miles per hour. The actual maximum level flight speed was 378 miles per hour at 23,500 feet, still exceptional performance for 1940, but speed alone did not make a combat aircraft. The prototype revealed handling characteristics that concerned Navy test pilots. The Corsair's long nose, necessary to accommodate the massive R2800 engine, created visibility problems during carrier approaches. The aircraft's high landing speed and tendency to stall suddenly made carrier operations dangerous. The wing's high lift meant the aircraft could achieve slow landing speeds, but the stall characteristics were unpredictable. Navy evaluators identified specific problems that needed resolution before the Corsair could enter service. Forward visibility was inadequate for carrier operations. Landing characteristics were unpredictable. The cockpit was positioned too far aft, creating balance and visibility issues. Insufficient during low-speed flight. Oil from the large engine covered the windscreen during certain flight attitudes. Vaught's engineering team spent the next 2 years refining the design. They raised the cockpit by 7 inches, improving pilot visibility. They modified the oil system to prevent windscreen contamination. They redesigned engine cooling baffles to improve airflow. They altered wing leading-edge slats to make stall behavior more predictable. The production F4U Corsair that emerged from these modifications was a substantially different aircraft from the prototype. Maximum speed reached 417 miles per hour at 19,900 feet. Service ceiling reached 36,900 feet. Combat range with external tanks exceeded 1,000 miles. Rate of climb was 2,890 feet per minute. Armament consisted of 6 Browning ANM 250 caliber machine guns mounted in the wings. The inboard, 4 guns carried 400 rounds each. The outboard 2 guns carried 375 rounds each. Total ammunition capacity was 2,350 rounds. The installation was designed for convergence at 1,000 feet, creating a cone of fire devastating to enemy aircraft. The Corsair's structure incorporated 150 pounds of armor plate protecting the pilot and critical systems. A bullet-resistant glass panel 1.5 inches thick provided additional cockpit protection. Self-sealing fuel tanks used multiple layers of rubber compounds that swelled when punctured, preventing catastrophic fuel loss from battle damage. These features reflected American design philosophy that prioritized pilot survival and aircraft durability. Japanese fighters had largely abandoned heavy armor in favor of lighter weight and better maneuverability. The Zero's early success seemed to validate this approach, but as American fighters grew more powerful, heavily armed, lack of protection became fatal. The United States Navy formally accepted the Corsair for operational service in 1942. Production began at Vaught's Stratford plant, with additional manufacturing at Goodyear and Brewster facilities. By early 1943, the first operational Corsairs were ready for combat deployment. Marine Fighter Squadron 124 received the first combat-ready aircraft in January 1943. The squadron, commanded by Major William Giese, began working up with their new fighters at Marine Corps Air Station in Miramar, California. Pilots who transitioned from older aircraft to the Corsair reported mixed impressions. The Corsair was faster and more powerful than any fighter they had flown. Visibility during taxiing and landing was poor due to the long nose. The aircraft demanded respect during carrier approaches. Engine torque from the massive propeller required constant rudder corrections. Once airborne and at combat speeds, the Corsair felt solid and responsive. On February 12, 1943, VMF 124 deployed to Henderson Field on Guadalcanal. The timing was significant. Guadalcanal had been secured by American forces, but Japanese air units still operated from bases at Rabaul and Bougainville. The Solomons campaign was entering a critical phase, where air superiority would determine the outcome of ground operations. The Marines at Henderson Field had been flying a mixture of F-4F Wildcats, P-40 Warhawks, and P-38 Lightnings. The Corsair was supposed to represent a qualitative leap forward, but the aircraft's combat debut would prove that superior technology alone could not guarantee victory. February 14, 1943, intelligence reports indicated a major Japanese raid forming over Bougainville, targeting Allied positions on Guadalcanal. VMF 124 scrambled along with other fighter units to intercept. The engagement became known as the St. Valentine's Day Massacre, though not for the reasons American planners had hoped. Japanese attackers included twin-engine bombers escorted by Zero fighters, flown by experienced pilots from elite naval units. The defending Americans included Corsairs making their combat debut, along with veteran units flying proven aircraft types. When the engagement ended, 9 American aircraft had been shot down. Japanese defenders lost only a single Zero fighter. The 9-to-1 loss ratio in Japan's favor was so severe that American commanders temporarily suspended daylight bombing missions to Bougainville pending tactical reassessment. For the Corsair, this first engagement seemed to validate critics who had questioned whether the aircraft's complexity was worth its promised performance advantages. Japanese pilots reported shooting down the new American fighters with relative ease. The bent-wing design that American engineers had created to solve propeller clearance problems appeared to offer no combat advantages. Radio intercepts indicated Japanese assessments ranged from dismissive to openly mocking. One pilot's transmission, later translated from captured documents, stated the Americans have sent another heavy fighter that cannot maneuver. Our Zeros will shoot them down as easily as the others. But the St. Valentine's Day engagement was misleading. American losses resulted not from aircraft inadequacy, but from tactical errors and inexperience. VMF 124 pilots were flying their first combat missions in an unfamiliar aircraft. They were attempting to dogfight with Zeros, playing to the Japanese fighters' strengths rather than exploiting the Corsair's advantages. The Zero excelled at slow-speed turning combat. Its light wing loading and relatively low power-to-weight ratio made it extraordinarily maneuverable below 250 miles per hour. In a turning fight at low altitude, an experienced Zero pilot could outturn almost any Allied fighter. The Corsair's strengths lay elsewhere. At high speeds above 300 miles per hour, the Corsair was faster, could dive more steeply, and could climb more rapidly than any Japanese fighter. The massive R2800 engine and efficient propeller design gave the Corsair performance advantages at high speeds that were impossible to match with lighter, less powerful designs. American pilots needed to learn tactics that exploited these advantages. Marine and Navy leadership recognized this immediately. New tactical doctrine emphasized what became known as boom and zoom fighting. Maintain altitude advantage over enemy fighters. Dive at high speed to attack, fire and break away before the enemy can respond. Use superior speed and climb rate to regain altitude. Never attempt to turn with a Zero at low speeds. These tactics were not intuitive to pilots trained in traditional dogfighting methods. They required discipline to break away from an engagement rather than pursuing a fleeing target into a turning fight. But once mastered, boom and zoom tactics transformed the Corsair from a vulnerable heavy fighter into a dominant predator. Second Lieutenant Kenneth Walsh of VMF 124 was among the first to master the new approach. On May 13, 1943, Walsh shot down his fifth enemy aircraft, becoming the first Corsair ace. His combat reports described the tactics that would become standard for Corsair operations. Patrol at 20,000 feet or higher. Maintain vigilance for enemy aircraft below. When targets are sighted, dive at maximum speed. Close to effective range, approximately 1,000 feet. Fire a short burst, 3 to 5 seconds. Break away using speed to disengage. Climb back to altitude using superior power. Repeat as ammunition and fuel allow. Walsh's success demonstrated what the Corsair could achieve in the hands of pilots who understood its capabilities. By August 1943, he had shot down 21 Japanese aircraft. His final score made him one of the top Marine Corps aces of the war. Other VMF 124 pilots adopted similar tactics with comparable success. As 1943 progressed, Corsair units in the Solomon Islands refined their operational methods. They learned to exploit the aircraft's strengths while avoiding situations that played to Japanese advantages. Combat loss ratios began shifting dramatically in favor of American forces. By mid-1943, Corsair squadrons were achieving kill ratios of 4-to-1 or better against Japanese fighters. The bent-wing design that Japanese pilots had initially dismissed was becoming associated with defeat and death. Japanese radio communications, intercepted by American intelligence units, revealed changing attitudes. Pilots who had mocked the Corsair in February were reporting in July that the American fighter was faster and could not be caught in a dive. Ground controllers at Japanese bases were warning pilots to avoid engagement with the bent-wing fighter unless they possessed significant altitude advantage. Intelligence assessments acknowledged that American pilot skill was improving and their tactics were more sophisticated. The turning point in perception came during the New Georgia campaign in July 1943. Corsair squadrons provided air cover for amphibious landings, flying hundreds of sorties from Henderson Field. Japanese attempts to interfere with the landings resulted in severe losses. On July 15, 1943, Marine Corsairs shot down 45 Japanese aircraft in a single day of operations. American losses were 7 aircraft. The 6-to-1 kill ratio represented a complete reversal from the St. Valentine's Day engagement 5 months earlier. More importantly, Japanese losses included experienced pilots who could not be easily replaced. American industrial capacity was producing both aircraft and trained pilots faster than Japan could match. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The tactical evolution of Corsair operations revealed something that Japanese observers initially failed to understand. The inverted gullwing was not merely a design quirk to accommodate a large propeller, it was the visible manifestation of design choices that gave the Corsair decisive advantages in the high-speed combat that was becoming dominant in Pacific air warfare. The wing's configuration allowed clean aerodynamic junction between wing and fuselage. This reduced drag at high speeds, contributing to the Corsair's exceptional maximum velocity. The short, strong landing gear that the cranked wing enabled meant less weight and less drag from gear doors and fairings. Weight savings translated directly into performance improvements. The large propeller that necessitated the unusual wing design was itself a critical advantage. The 13-foot 4-inch Hamilton Standard hydromatic propeller was the most efficient ever fitted to a fighter. It converted engine power into thrust with minimal losses. At high speeds, where propeller efficiency typically degraded, the Corsair's propeller maintained effectiveness that smaller propellers could not match. Japanese fighters used smaller propellers by necessity. Their engines produced less power, requiring smaller diameter propellers to maintain proper RPM. Smaller propellers were less efficient at high speeds, creating a performance deficit that compounded as velocities increased. At 400 miles per hour, the Corsair's propeller efficiency advantage became decisive. The R2800 double Wasp engine produced consistent power across a wide altitude range. The two-stage supercharger maintained manifold pressure as air density decreased with altitude. At 20,000 feet, where Japanese fighters began losing power, the Corsair's engine was still producing over 1,800 horsepower. This power advantage translated into climb rate superiority that had profound tactical implications. In combat, altitude equals energy. The side that can climb faster can choose when and where to engage. Corsair pilots operating from 25,000 feet could dive on Japanese formations at 20,000 feet, attack, and climb back to safety faster than enemy fighters could pursue. Japanese pilots found themselves trapped in an impossible tactical situation. If they climbed to match Corsair altitudes, the climb took longer and consumed more fuel, leaving less time for combat operations. If they remained at lower altitudes where their aircraft performed better, they ceded the initiative to Corsair pilots who could attack from above at will. The combat records from late 1943 and early 1944 documented this dynamic with brutal clarity. Japanese loss rates increased while their claims of American aircraft destroyed decreased. Air superiority in the Solomon Islands passed decisively to American forces. The Corsair was central to this shift. By December 1943, 12 Corsair squadrons were operating in the South Pacific. They had collectively shot down over 400 Japanese aircraft, while losing fewer than 50 Corsairs to enemy action. The 8-to-1 kill ratio exceeded the performance of any other Allied fighter in the theatre. More Corsairs were being lost to operational accidents than to enemy action. The aircraft's challenging handling characteristics during landing continued to cause crashes. Pilots who lost concentration during carrier approaches could find themselves in unrecoverable situations. The long nose created blind spots that made formation flying demanding. Engine failures on takeoff were often fatal due to the Corsair's high wing loading and resulting poor single-engine performance. These operational challenges led the Navy to initially restrict Corsair operations to land-based units. Marine squadrons operating from island airfields could accept the aircraft's difficult handling because they were not attempting carrier operations. Navy carrier squadrons continued flying the older but more forgiving F-6F Hellcat. The decision was pragmatic, but it meant that the Corsair's combat debut was delayed in the most critical theatre. The fast carrier task forces that would strike Japanese positions across the Central Pacific in 1944 would do so without the most capable fighter available. Marine squadrons would continue fighting from island bases, achieving remarkable success, but not participating in the mobile carrier warfare that would decide the Pacific campaign. This situation would change in late 1944 when operational necessity forced the Navy to reconsider. But through most of 1943 and into 1944, the Corsair remained primarily a Marine Corps aircraft fighting from land bases, while the Navy relied on other fighters for carrier operations. Japanese intelligence officers monitoring American air operations noted this distinction. Their assessment was that the bent-wing fighter was too difficult to operate from carriers, supporting their view that it was a flawed design. This assessment would prove catastrophically wrong, but it reflected Japanese attempts to understand why Americans were using their most capable fighter only from land bases. The answer was not design flaws but operational doctrine. The Navy's assessment was that F-6F Hellcats provided adequate performance with better handling characteristics for carrier operations. Marine squadrons accepted the Corsair's challenging nature because its performance advantages were decisive in the missions they flew. As 1944 began, the Corsair's reputation in the Pacific was firmly established. Japanese pilots had learned to respect and fear the bent-wing fighter. American industrial production was accelerating, with multiple factories producing Corsairs in increasing numbers. Improved variants were entering service with more powerful engines, better armament, and refined handling characteristics. The stage was set for the Corsair to demonstrate its capabilities on a larger scale. The Central Pacific Offensive was about to begin, driving toward the Philippines, Iwo Jima, and eventually Japan itself. Corsair squadrons would fly from captured islands, supporting each amphibious operation with close air support and air superiority missions. What Japanese engineers and pilots did not yet understand was that the Corsair's advantages extended far beyond its speed and power. The aircraft's robust structure, heavy armament, and ability to carry external ordnance made it an exceptionally versatile platform. It could perform fighter missions against enemy aircraft, ground attack missions against enemy positions, and even anti-shipping strikes against Japanese vessels. This versatility would become increasingly important as American forces advanced toward Japan. The Corsair would prove capable of missions that no Japanese fighter could match, demonstrating that the bent-wing design was not a compromise but an integrated solution to multiple requirements. The island of Peleliu, September 19, 1944. Marine Corsairs from VMF 114 and VMF 121 circled above the invasion beaches as landing craft approached the hostile shore. The fighters were not hunting enemy aircraft. They were carrying bombs and rockets, preparing to strike Japanese defensive positions that threatened the amphibious assault. This mission profile represented the Corsair's evolution from pure fighter to multi-role combat aircraft. Each Corsair carried either a 1,000-pound bomb on the centerline rack or 8 5-inch high-velocity aircraft rockets under the wings. The bent-wing fighters that Japanese intelligence had dismissed as overly complex were now delivering ordnance with precision that no Japanese aircraft could match. The ground attack mission had not been part of the original design requirements. The Navy's 1938 specification called for a fighter, not a fighter-bomber, but the Corsair's robust structure and powerful engine created load-carrying capacity that Vaught's engineers recognized could be exploited. External ordnance racks were developed and tested through 1943. By early 1944, Corsairs were regularly carrying bombs and rockets on combat missions. The aircraft's strength meant it could deliver heavy ordnance without compromising structural integrity. The R-2800 engine provided enough power to maintain acceptable performance even with external stores. Most importantly, the stable flight characteristics at high speeds made the Corsair an effective dive bomber. Japanese defensive positions on Pacific islands were typically reinforced concrete bunkers and cave systems that could withstand naval bombardment. Destroying these positions required precision strikes with heavy weapons delivered from aircraft. The Corsair proved exceptionally capable in this role. Marine pilots developed tactics for dive bombing that exploited the aircraft's characteristics. Approach the target at 15,000 feet, roll inverted and pull through into a vertical dive. Release ordnance between 2,000 and 1,500 feet. Pull out of the dive using the aircraft's structural strength to sustain high G loads. Climb away at maximum speed while the wingman attacked. The accuracy achieved by experienced pilots was remarkable. Bombs could be placed within 50 feet of the target from release altitudes that kept the aircraft above most anti-aircraft fire. The 5-inch HVAR rockets, high-velocity aircraft rockets, were equally effective against point targets. Each rocket carried a warhead comparable to a 5-inch naval shell. 8 rockets delivered the equivalent of a destroyer's broadside. During the Peleliu operation, Marine Corsairs flew over 600 close air support sorties in the first week. They destroyed dozens of Japanese bunkers and gun positions that were holding up the ground advance. Infantry commanders reported that Corsair strikes were more effective than naval gunfire for neutralizing fortified positions because aircraft could attack from angles that naval guns could not achieve. The Japanese garrison on Peleliu had prepared for American invasion with typical thoroughness. They had constructed elaborate defensive works designed to inflict maximum casualties. What they had not anticipated was the level of precision air support American forces could bring to bear. Corsairs orbiting above the battlefield could respond to ground controller requests within minutes, striking targets with accuracy that made Japanese defensive positions untenable. This close air support capability became the Corsairs' most valuable contribution to the island campaigns of late 1944 and 1945. At Iwo Jima in February 1945, Marine Corsairs flew over 2,000 close air support sorties. At Okinawa in April through June 1945, the number exceeded 5,000 sorties. Infantry units began referring to the Corsairs as Angels of Okinawa for the life-saving support they provided. Japanese forces, attempting to understand why their defensive positions were being systematically destroyed, struggled to grasp the integration of American air and ground operations. Their own close air support capabilities were limited by lack of coordination systems, inadequate radios, and aircraft that were not designed for precision ground attack. The Corsairs' versatility extended to anti-shipping strikes. In the Philippines campaign, Corsair squadrons attacked Japanese vessels with rockets and bombs. The stable platform and heavy armament made the Corsair effective against ships that Japanese aircraft struggled to damage. 5-inch rockets could hold destroyer hulls below the waterline. 1,000-pound bombs could break the backs of merchant vessels. On December 7, 1944, exactly 3 years after Pearl Harbor, Corsairs from Marine Air Group 12 attacked Japanese shipping in Ormoc Bay, Philippines. They sank 3 cargo ships and damaged 2 destroyers. Japanese naval forces operating in Philippine waters found themselves vulnerable to air attack, even when American carriers were not nearby because land-based Corsairs had the range and ordnance capacity to reach them. The Pacific War was creating demands that no aircraft designer in 1938 could have anticipated. The Corsair was meeting those demands because its fundamental design was sound. The powerful engine provided margins for growth. The strong structure allowed modifications without compromising safety. The efficient propeller and clean aerodynamics maintained performance even with external stores. Japanese aircraft designers facing similar operational demands found their designs had less growth potential. The Zero and other fighters, optimized for lightweight and maneuverability, could not easily be modified to carry heavy ordnance. Attempts to upgrade engines ran into structural limitations. The design philosophy that had created success in 1941 became a liability by 1944. Meanwhile, the Corsair continued evolving. The F4U-1D variant, introduced in April 1944, featured a more powerful R2800 engine, producing 2,250 horsepower. Maximum speed increased to 446 miles per hour. The later F4U-4 variant would reach 462 miles per hour, making it one of the fastest piston engine fighters of the war. Armament improvements accompanied engine upgrades. The F4U-1C variant, replaced the 650 caliber machine guns with 4 20mm cannons. Each cannon carried 201 rounds. The 20mm shells were far more destructive than 50 caliber bullets, particularly against aircraft with armored components or against ground targets. Many pilots preferred the 50 caliber armament for its ammunition capacity and reliability. The 6 guns with 2,350 total rounds provided longer firing time than 4 cannons with 804 total rounds. But the cannons were devastating when they hit. A single 20mm shell could destroy a fighter or set a bomber ablaze. The debate over armament reflected broader questions about aircraft design philosophy. Japanese fighters typically carried 2 20mm cannons and 2 rifle-caliber machine guns. This mixed armament provided some heavy hitting power while maintaining lighter weight. American fighters increasingly standardized on either all 50 caliber guns or all 20mm cannons for consistency in ballistics and ammunition supply. The Corsair's ability to carry either armament package demonstrated design flexibility. The wing structure could accommodate the heavier cannons without modification. Ammunition boxes fit in the existing space. Pilots and squadrons could choose configurations based on mission requirements. Fighter escort missions favored 50 caliber guns for ammunition capacity. Ground attack missions favored 20mm cannons for destructive power. By mid-1945, Corsair production had reached industrial scale that Japanese aircraft industry could not approach. Vought, Goodyear and Brewster factories were producing over 400 Corsairs per month. Total production would eventually exceed 12,500 aircraft. Every production, Corsair included improvements and refinements based on combat experience. The industrial capacity represented by this production was as significant as the aircraft's design. Each Corsair required thousands of precision components manufactured to tight tolerances. The R2800 engine alone contained over 2,000 parts. The Hamilton Standard propeller was a masterpiece of mechanical engineering. Radios, instruments, hydraulic systems, electrical systems, and flight controls all had to work together reliably. Japanese industrial capacity was declining through 1945 as American bombing destroyed factories and disrupted supply chains. Aircraft quality deteriorated as skilled workers were conscripted and substitute materials replaced proper specifications. By contrast, American production was increasing with quality improving as manufacturing processes matured. This industrial disparity meant that even if Japanese designers had created aircraft equal to the Corsair, they lacked the capacity to build them in necessary numbers with required quality. The war had become a contest on production as much as combat. American industry was winning decisively. The Corsair's combat record through 1945 reflected this material superiority. Marine and Navy squadrons were achieving kill ratios consistently above 10-1. Japanese pilots with adequate training and fuel could still fight effectively, but such pilots were increasingly rare. Most Japanese aviators by 1945 had minimal training, inadequate aircraft, and insufficient fuel for effective combat operations. On April 7, 1945, Marine Corsairs participated in Operation Ten-Go, the interception of the Japanese battleship Yamato during its final sortie. While carrier-based aircraft delivered the attacks that sank the battleship, land-based Corsairs provided combat air patrol that prevented Japanese aircraft from interfering. The mission demonstrated the Corsair's range, capable of operating hundreds of miles from base with sufficient fuel for combat. Japanese attempts to counter the Corsair through the final months of war were ineffective. New fighter designs like the Kawanishi N-1K Shiden or George in Allied reporting were too few and entered service too late. Kamikaze tactics that relied on overwhelming defenses through mass suicide attacks achieved some success against ships, but Corsair combat air patrols shot down hundreds of kamikaze aircraft before they could reach targets. The bent-wing fighter that Japanese intelligence had dismissed in February 1943 had become synonymous with American air superiority. Japanese pilots who survived encounters with Corsairs reported that the American fighter was faster, more heavily armed, better protected, and flown by increasingly skilled pilots. there was no effective counter within Japanese capabilities. The final accounting of the Corsair's combat effectiveness came after the war, when American and Japanese records could be compared. The numbers were stark and undeniable. American pilots flying Corsairs had shot down 2,140 Japanese aircraft during World War II. Corsair losses to enemy action totaled 189 aircraft. The kill ratio was 11.3 to 1. These numbers exceeded the performance of almost every other fighter in the war. The only Allied fighters with comparable ratios were the P-38 Lightning and F-6F Hellcat, both of which benefited from similar American advantages in pilot training, logistics, and industrial support. No Japanese fighter achieved better than 3-to-1 ratios in any sustained campaign. The statistics revealed something deeper than tactical success. They demonstrated the compound advantages of superior design, industrial capacity, pilot training, and operational support. The Corsair was an excellent aircraft, but its combat record also reflected everything America brought to the Pacific War. Japanese engineers, who later examined captured Corsairs, understood this. In reality, in early 1945, Japanese forces recovered at least one intact Corsair after the pilot was forced to ditch following engine failure. The aircraft was transported to the Yokosuka Naval Air Technical Arsenal south of Tokyo for examination. What Japanese specialists discovered during their analysis confirmed suspicions that had been growing throughout the war. The Corsair represented manufacturing sophistication and material quality that Japanese industry could not match. Every component showed precision machining and consistent quality. Aluminum alloys had uniform properties. Engine components were manufactured to tolerances measured in thousandths of an inch. Even small fasteners were made to standards that exceeded typical Japanese specifications. The examination focused initially on the inverted gullwing that made the Corsair instantly recognizable. Japanese engineers understood the aerodynamic and structural logic of the design. The cranked wing allowed short landing gear while providing propeller clearance. The compound angles created efficient wing fuselage junctions with minimal drag. The structural loads distributed through the wing were optimal for strength with minimum weight. But understanding the design was different from being able to manufacture it. Creating the compound curves of the inverted gullwing required sophisticated tooling and quality control. Each wing had to match its counterpart precisely, or the aircraft would have asymmetric flight characteristics. The precision required exceeded what most Japanese factories could achieve reliably, particularly by 1945 when industrial capacity was deteriorating under American bombing. The wing structure revealed construction methods that impressed Japanese specialists. The main wing spar was a massive forging of exceptional quality. American metallurgy had produced aluminum alloy, with strength characteristics Japanese facilities struggled to match. The ribs stamped from aluminum sheet showed remarkable consistency. Each component was virtually identical, indicating manufacturing with tight quality control. Japanese aircraft production increasingly struggled with consistency. Individual aircraft showed variations in component quality as wartime pressures forced compromises. The Corsair represented industrial processes, where quality was maintained despite mass production. This was perhaps more significant than any single design feature. Attention turned to the massive Pratt & Whitney R2800 engine. Japanese engineers had encountered this engine before in other captured aircraft, but never in reasonably intact condition. The engine's construction revealed manufacturing capabilities that seemed almost incomprehensible. Cylinders were precisely machined with tolerances measured in thousandths of an inch. Pistons, connecting rods, and crankshaft components showed surface finishes and dimensional accuracy that Japanese engine manufacturers struggled to achieve. The two-stage supercharger system, designed to maintain power at high altitudes, incorporated complex internal passages and precisely fitted rotating components. Japanese attempts to develop comparable superchargers had largely failed due to manufacturing limitations. Even when Japanese engineers understood the theoretical principles, they lacked the industrial capacity to produce components with necessary precision. The engine's reliability was as impressive as its power output. American radial engines routinely produced their rated horsepower for hundreds of hours between overhauls. Japanese engines, even new examples, often failed to achieve theoretical power ratings and required frequent maintenance. The R-2800's consistent performance came from superior metallurgy, better lubricants, more precise manufacturing, and sophisticated quality control. The Hamilton Standard hydromatic propeller, with its 13-foot 4-inch diameter and variable pitch capability, represented advanced aerodynamic design and hydraulic control. The propeller automatically adjusted blade angle based on flight conditions, optimizing performance without pilot input. Japanese engineers understood propeller theory, but lacked facilities capable of producing large propellers with necessary precision. Throughout the aircraft, Japanese specialists found consistent patterns. Every system showed sophisticated engineering and quality manufacturing. The landing gear mechanism was complex, but precisely made. The cockpit instruments were comprehensive and clearly laid out. The fuel system incorporated self-sealing tanks using multiple rubber compound layers that swelled when punctured. The electrical system was well designed with proper wire routing and insulation. Perhaps most revealing was the overall impression of quality. The aircraft felt substantial, well-made, built to withstand the stresses of combat and carrier operations. This quality stood in sharp contrast to Japanese aircraft production in 1945, where shortages had forced increasing use of substitute materials. Aluminum quality had deteriorated, skilled workers had been conscripted, and factories operated under constant threat of American air raids. Japanese technical personnel wrote reports documenting their findings. The reports were professional and detailed, describing measurements and manufacturing techniques. But the underlying message was unavoidable. In nearly every category examined, American technology exceeded Japanese capabilities. The gap was not small or easily closed. It represented years of industrial development, massive investments in research, sophisticated supply chains, and resources Japan simply did not possess. The bent-wing fighter that Japanese pilots had initially dismissed revealed itself as evidence of engineering excellence and manufacturing sophistication that Japanese aviation had been confronting throughout the war. The inverted gullwing was not a design flaw or unnecessary complication. It was the visible signature of an aircraft designed to accomplish multiple missions with a level of performance that Japanese fighters could not match. By the time Japanese engineers were examining the captured Corsair, the war was effectively over. American B-29 bombers were systematically destroying Japanese cities. The Navy had been shattered at Leyte Gulf. The Philippines had been liberated. Iwo Jima had fallen, and Okinawa was in American hands. In this desperate context, the technical examination took on somber significance. It was not intelligence gathering for future victories, but a final reckoning with technological reality. Japanese specialists could measure the performance gaps, analyze the manufacturing differences, and calculate the resource disparities. Their reports stood as acknowledgement of Japan's failed attempt to match American industrial might. When American occupation forces arrived at Yokosuka Naval Air Technical Arsenal in September 1945, they found extensive evidence of Japanese technical intelligence efforts. Captured Allied aircraft were scattered around the facility. Technical reports, drawings, and photographs documented Japanese attempts to understand Allied technology. American intelligence officers collected these materials, recognizing their value for understanding what Japan had learned. The Corsair itself went on to long service beyond World War II. The aircraft that had been designed in 1938 continued flying combat missions into the 1960s. During the Korean War, from 1950 to 1953, Corsairs proved effective in ground attack and close air support roles, even as jet fighters took over air superiority missions. Marine and Navy squadrons flew thousands of Corsair sorties in Korea. The aircraft's ability to carry heavy ordnance loads and operate from rough airfields made it valuable for supporting ground forces. Pilots who had flown Corsairs in World War II returned to combat in the same aircraft type, now attacking Chinese and North Korean positions instead of Japanese targets. Foreign air forces continued operating Corsairs long after American forces retired them. France flew Corsairs in Indochina and Algeria through the 1950s. The French Navy operated F4U variants specifically built for their requirements, featuring more powerful engines and improved armament. These aircraft saw extensive combat in colonial conflicts. The final combat missions flown by Corsairs occurred during the Soccer War between Honduras and El Salvador in July 1969. On July 17, 1969, Honduran Captain Fernando Soto, flying an F4U-5, shot down 3 Salvadoran aircraft, including 2 FG-1D Corsairs. The engagement was remarkable because it represented the last combat victories achieved by Corsairs, ironically against other Corsairs. From first flight in 1940 to final combat missions 29 years later, the Corsair proved one of aviation history's most successful and long-lived fighter designs. Total production exceeded 12,500 aircraft. The type served with distinction in 3 wars. Pilots consistently praised its performance, reliability, and survivability. For Japan, the encounter with the Corsair was part of a larger reckoning with technological reality. Japanese engineers and scientists who had struggled against material shortages and industrial limitations during the war now worked with American occupation authorities to rebuild Japanese industry. Lessons learned from examining American technology influenced post-war Japanese manufacturing philosophy. The emphasis on quality, precision manufacturing, and continuous improvement that characterizes modern Japanese industry has roots in the hard lessons learned when Japanese engineers examined what American industry could produce. The Corsair's precision components, consistent quality, and sophisticated systems demonstrated standards that became goals for post-war Japanese manufacturing. The bent-wing fighter that Japanese intelligence had dismissed in February 1943 had revealed itself as more than just a successful combat aircraft. It was evidence of an integrated approach to warfare that combined design excellence, industrial capacity, tactical innovation, and operational support into a system that Japan could not match. The 2,140 kills against 189 losses represented not just aerial combat victories, but the compound advantages of every element working together. Superior aircraft flown by well-trained pilots, maintained by skilled ground crews, supplied with adequate fuel and ammunition, supported by effective logistics, and directed by competent commanders, achieved results that no single factor could explain. Japanese forces had fought with courage and determination throughout the Pacific War. Their pilots had demonstrated skill and dedication that earned respect even from enemies. But courage and skill could not overcome the massive technological and industrial advantages their opponents possessed. The Corsair was one piece of a larger American war machine that combined innovation, production, and operational effectiveness into an overwhelming force. The story of the Corsair's bent wings is ultimately the story of how integrated systems triumph over isolated capabilities. The inverted gullwing was not just a solution to propeller clearance. It was part of a design that balanced competing requirements into an aircraft that could fight, bomb, rocket ground targets, escort bombers, defend ships, and operate from carriers or island airstrips with equal effectiveness. Japanese aircraft designers had created excellent fighters for specific missions. The Zero was superb for its intended role, but the rigid specialization that made Japanese fighters effective in 1941 became a fatal limitation as the war's demands evolved. The Corsair's versatility allowed it to adapt to changing requirements, taking on missions its designers never anticipated. The final lesson Japanese engineers took from examining the Corsair was perhaps the most important. Modern warfare demanded not just good weapons, but flexible systems capable of evolving with changing circumstances. The bent-wing fighter represented a design philosophy that built in margins for growth, anticipated future requirements, and accepted complexity when complexity enabled effectiveness. This philosophy would influence post-war aviation development worldwide. The era of specialized fighters optimized for single missions was ending. Future aircraft would need to perform multiple roles effectively. The Corsair had demonstrated both the possibility and the necessity of this approach. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.